Right. Hello, everybody. Good afternoon. So my name is Tao Han from the University of Pittsburgh. I'm the director of Pittsburgh Particle Physics, Astrophysics, Cosmology Center. I have been a general member of Aspen Center for Physics for about 8 years, and maybe 2 more years to be on. So it's you earn it, not the old time. So welcome to our free public lecture, which is sponsored by Nick and Maggie DeWolf Foundation, which has been sponsoring this lecture series in Aspen for the past 30 winters. So their generosity, as well as a contribution from all our speakers, made this possible, and to share the most recent new research results. That is the important aspect to move science forward. So this is our way of thanking you all, our Aspen community, to support this center. Thank you very much. So each year, during the winter time in January, February, and March, groups of physicists, up to 110, will spend an intensive week here, like this week, here to share their latest research results and to discuss with their colleagues in very formal meetings, but also in very informal conversations, and even on the lifts, the cross-country trails, and even on snowshoes. So it's very enjoyable and for discussing physics with your colleagues as well. So I'm here this week participating in this conference named as Prospecting New Physics Through Dark Matter and Machine Learning. So we are particle physicists here this week. So we work on theoretical and experimental high-energy physics, addressing fundamental questions such as the origin of mass and the nature of forces, matter-antimatter asymmetry imbalance, the search for dark matter and dark energy, and so on and so forth. So despite the long days, but we always left the refreshed new ideas, and Aspen is the most inspiring place we can think of, both in the winter and as well in the summer. So tonight, we are very fortunate to have a Professor Tim Tait from the University of California to give us this public lecture. Professor Tim Tait is a Chancellor Professor and Chair of the Department of Physics and Astronomy at the University of California, Irvine. His research interests are very broad. That includes theoretical investigations of physics beyond the standard model of particle physics phenomenology, and high-energy collider physics, and cosmology. His works involve both exploring new models and new phenomena, as well as a theoretical interpretation for new experimental results. Tim received his bachelor degree in physics from the University of California, San Diego, and then received a Ph.D. degree in physics from Michigan State University. He did his postdoc research in particle physics groups at the Argonne National Lab and the Fermilab. So he's a fellow of American Physical Society, recipient of Friedrich Wilhelm Awards from the Alexander von Humboldt Foundation, and also a winner of APS, American Physical Society Division of Particle Fields Mentorship Award in 2019. The last but not least, Tim has been a great colleague and dear friend of mine for the more than 3 decades. All right, almost true. Yeah. So we have been together for a lot of physics discussions and collaborations. I have never seen him to be angry. Oh, it's a Canadian. He continues to serve as a department chair after his first term just because his friend wanted him to. He's such a nice, generous person. And still, I owe him unlimited beer for a good reason. One time I was organizing conference proceedings, and which are called the TASI proceedings held in Boulder, Colorado. And he was the first one to submit the contributions. For that, I thank him very much. So of course, I have a lot of stories about Tim, but without overdue, let me turn this over to Tim to give us this public lecture. Please join me to welcome Tim. Thank you very much.
Thank you so much for that very warm welcome. And thank you to Tao for that great introduction. I'll tell you, it's not 3 decades, it's a little bit more than 2 decades. And after the first time I met Tao, I went home I told my wife, who's also a physicist, "Can you believe it? I met Tao Han today." Oh, it has been a long time. Also, just to co-opt one question that I'm sure you're going to have at the end of this talk, and I can answer it right now. In case you're wondering, this animal is an anteater. It's the mascot of UC Irvine. Cannot tell you exactly why it's the mascot of UC Irvine, but apparently this is what happens when your campus, born in the 1960s, you let your students vote on what the mascot's going to be. Okay. All right. So I'm going to talk about dark matter, and I'm going to build this up by introducing first why we need dark matter, and then what it is, why it is that a bunch of particle physicists who are not astronomers, or at least not all of us are astronomers, are so interested in it and talking about it this week during our workshop. I wanted to start with this very beautiful picture I found. This is a picture of our galaxy. It's actually taken from a desert in northern Africa, and you can see, of course, the Milky Way that most of us have seen. Here in Aspen, we're lucky. We actually get a chance to see it more often than we do in other parts of the world, frequently. And of course, the visible part of the Milky Way is impossibly big. This together looks like a glow to us, but it's actually more than 100 billion stars like the sun. It is incredible how immense it is. And it's shaped more or less like a disk. The sun is in kind of this uninspired place, not at the center, not at the edge. Just right, maybe? I don't know. Of course, if you look at it edge on, which is how we see it, because we live inside the disk, that's why you get something that looks like a line in the sky. We're actually not looking at it from above like this image is recreating. We're looking at it inside it, the edge. The visible parts of the Milky Way is impossibly big, and yet it's actually not at all the whole story of what our galaxy is. So here is Bill Waterston's, if I can move this, Calvin and Hobbes comic about this. It really is inspiring when you look at the sky and you realize actually much smaller than a speck of dust. Nonetheless, we're very, very interesting specks of dust because we're the specks of dust that actually ask questions. Right. So, as I said, though, the stars in the galaxy are not even the half of it. The part that we can see, the stars and some dust using telescopes, is actually only about 5% of the total mass that makes up the galaxy. So if you could actually see the galaxy weighted by mass, it would be much, much larger than the part that you can see. And it's made of something that's invisible to our telescopes, which stretches out far, far beyond the limits of where we can see stars, kind of like a giant diffuse halo around the galaxy. And it's reasonable to ask, okay, that's a pretty amazing claim. Do we actually know that it's true? We have overwhelming evidence that this is true. And we know this, I'm going to explain a couple of them that just sort of give you a flavor for how this works. So we know this basically because we can look at the different objects in the galaxy. And so here I've just highlighted a few at random. Our telescopes can measure them. They can determine where they are in the galaxy and how fast they're moving. And we can ask, okay, we know that gravity is supposed to be holding this whole galaxy together and making it move the way it does. So does gravity actually explain the motion of these objects that we can measure? And it turns out it can't. You just add up all the things that we can see and then compute the force of gravity that it would exert any one of these things, find out it's not enough to actually explain how they're moving. So, if you think about this as kind of like a cosmic scales, you know how much gravity it would take to make this star move in this direction with this speed. Then I add up the whole galaxy, find out how much it would pull on that star and ask, is it pulling enough? And the answer is not nearly enough. When we add up the stars, we don't get enough. If we add in the gas that we can see, it helps a little bit, but it's still not nearly enough. So it's only when we add the dark matter, which is 20 times more in mass than these other things, it actually balances out. Then at that point, we get a map of roughly where the dark matter is, and we get know that it's here and pulling on these things and making them move the way we see. All right. One other thing I wanted to mention in terms of motivating the existence of dark matter has to do with cosmic structure. And so I'm going to show you this by showing you a movie. The movie is a simulation that actually shows us what we think happened in the very earliest moments of the universe, right after the Big Bang, when the galaxies formed. So we think, in fact, we have very good evidence that at this moment, the stuff in the universe was pretty smooth. it was spread out pretty evenly. It wasn't clustered together to make stars and planets and us, things like that. It was actually just very evenly spread throughout, with very, very tiny fluctuations in terms of maybe a little bit more here and a little bit less there. This is a simulation which was done by James Bullock and his group at UC Irvine. It starts out tracking the matter in the universe after the Big Bang. This timer is going to count down from this initial point, 0. 0 is actually the time of the universe today. This is how many years ago, how many billion years in the past we are. So if we start it going, and it's rotating around just so you can see it a little better, you can see that matter is starting to cluster together because gravity is pulling it together. Now it's starting to form interesting structures. You can see that there are some hot spots. There are these interesting threads that kind of link them together. Hot spots don't come by themselves. They're very clustered. There's lots of them all together and all moving around in a kind of a cosmic dance. We're still actually nowhere near today on this simulation, by the way. Now it's rotating the other way, just so you can see it, other parts of it. But now it's starting to look a lot like the universe that we see today, in the sense that we see galaxies, we see stars in them, and we see the galaxies clustering together. Okay. So that's what a universe looks like if we actually build it out of dark matter. If we look with telescopes, this is an image from the Very Large Telescope. You get, unfortunately, it's a pretty crude image because we just don't have a great picture. But these are pictures of galaxies. The bright galaxies are these little white dots here. And we can see that there is some gas that is linking them together. And so what happens is the dark matter clusters together and forms these structures. So if you look at this, with a little imagination, you can imagine these two images actually look a lot alike. You have clusters of galaxies together. You've got, in different areas. Then you have these filaments kind of joining them. And so what's happening is visible things that we can see, like the stars and the gas, are actually being pulled by the gravity of the dark matter, and they trace where it is. Even though we can't see the dark matter directly, at this very large distance scales, looking at whole galaxies, we can actually, you can see where it has to be because this is where it's pulled ordinary matter in. And if we tried to run the simulation without dark matter, it would look totally different. There wouldn't be enough gravity and it wouldn't pull things together. We wouldn't see so many galaxies clustered together. We wouldn't see so many of these filaments linking them. And just to give you some perspective, our whole galaxy in this simulation is just a tiny, tiny little thing. You go on YouTube, you can find a lot of videos like this that are interesting to look at. All the comments say the same thing. This looks like neurons in a brain, which I think is fascinating. I don't think there's any physics in it that I'm aware of, but what can I say? I would love to know what that brain was thinking. Okay, so I'm going to switch gears now and get to the main topic that I wanted to discuss, and that is the topic of dark matter and how to fit it into a more fundamental theory of physics. So we just saw that observations tell us that not only do we need dark matter, it turns out if you put all the observations together, it's pretty clear we need about 5 times more dark matter than ordinary matter to explain the universe. In terms of the cosmic pie chart, stuff that we're made of, the stuff we understand is just this little tiny sliver. Dark matter is this pretty big piece of the pie. The rest of it's dark energy, which I'm actually not going to talk about today. This has inspired all sorts of things in the art world. So here's the question. If 2% milk is 2% milk fat, why is whole milk 3.5%? What's the rest of it? And of course, if you're a physicist, the answer is it's about 27% dark matter and the rest is dark energy. Luckily, it doesn't have any calories. So. Right. So then the question is, what the heck is this dark matter stuff anyway? And to answer that, and how is it related to the other fundamental constituents of the universe? And to answer that, I've got to tell you a little bit about what we know about ordinary matter and the ordinary particles that we understand very well, and then see how these two things can be fit together. So to do that, I have to talk about the standard model of particle physics. The standard model of particle physics describes all of the fundamental matter and the forces that we know. This is kind of like the periodic table for fundamental physics. And if you took these different particles together, and you're going to see how to do that in 1 second, you can actually build the entire periodic table that you actually learned about in middle school out of these particles. A few of them. You don't actually need that many of them, but they're all there. So the quarks and the gluons up here and over here, they make up protons and neutrons, and those are the things that make up nuclei. So that's a big part of the periodic table. It's actually organized based on how many protons and neutrons there are, how many protons really there are in the nucleus. They're held together. A proton is two up quarks and a down quark. And the interesting theory of quantum field theory, which describes these fundamental interactions, the way that two quarks know about each other is they're constantly shooting gluons at each other. That tells each other that they are there, and that's how they know they're supposed to be stuck together into a proton. Leptons that live down here in this part of the table include the electron. So the electron is the other part of the atom. The reason why there are chemical bonds is because different atoms can share electrons together. The electron has some heavy cousins, which are pretty mysterious. We don't really know why those are there, but we can see them. And also has even more mysterious partners like the neutrinos. And I've also highlighted here photon. The photon is the particle that transmits electromagnetic interaction. Again, we all learn that when two electrons, so here's an electron coming in this way, here's another one coming in the other way, they should repel each other because they both have negative electric charge. And again, quantum field theory says they're doing this because they're throwing photons back and forth that say, I'm negative, and the other guy says, I'm negative. And as a result, they repel from each other. W and Z particles transmit the weak nuclear force. We can understand why the neutron actually has radioactive decay into a proton, an electron, and a neutrino, because it's actually emitting a W particle. Of course, inside the proton and neutron, what it really is a down quark is turning into an up quark. And the other quarks are moving along for a ride. And the Higgs, which was discovered in 2012 at the Large Hadron Collider in Switzerland, provides masses to all these fundamental particles. That's a whole separate talk that I'm not going to be able to say anything about. You came to one of these talks in the summer, then Marcela Carrena, who's sitting in the front of the room, actually told you all about it already. Okay, so the first question then is, we have all these great particles, we know a lot about them. Would one of these particles actually be the dark matter? And spoiler alert, the answer is no. But to make sure that we understand that well, we should ask, what do we know about dark matter? Dark matter is, well, dark. That means it doesn't emit light, and that means that it doesn't have electric charge. Particles with electric charge actually emit light very easily. It has to be moving very slowly, and that's because we need it to clump together and form galaxies like we saw before. Usually we take this to mean that it's heavy, but strictly speaking, it doesn't have to be heavy, it just has to be moving very slowly. And it's still around today. And so that means it's stable or has a lifetime at least as big as the age of the universe itself. Turns out it has to have a lifetime way, way more than that, or we would already know it. So I call this the dark matter questionnaire. These are all the things that we don't know about dark matter. So, as you find them out, you get to put in a little checkbox. I didn't watch Futurama, but apparently this guy was made out of dark matter. So if you see him, give him the questionnaire, make him fill it out. Because all that we know so far is that it actually talks to gravity. We don't know anything else. Okay, so nothing works. Most of the particles here are electrically charged, and that means they shine, they emit light, they're not dark matter. Some of the remaining ones are too light. They're not heavy enough. And so as a result, it wouldn't clump together and form galaxies like we need them to. There's only two left. You can see the Z boson and the Higgs boson, but both of those are very radioactive. They decay extremely quickly. In fact, so quickly that we've never even been able to have them in our hands, just see what they decay into, and that's how we know that they were there in the first place. So there's nothing that works in the standard model. That means that dark matter has got to be physics beyond the standard model. And the fundamental question for particle physics is, how do we put the dark matter into this table? Where does it belong? I mean, we know it's not like any of these particles, but it's close to being like some of them. Maybe it's actually related to them in some way. And that's a big area of theoretical activity, is just trying to understand how it is you could possibly put the dark matter into this picture and then try to figure out whether that's right or not. So do we have any good ideas for what dark matter could be? Here's one from the art world. This is a sculpture. It's at the Tait Modern Museum. Now, if you notice very closely, Tait is spelled incorrectly, so don't be confused if you go to London and try to see it. It's a three-dimensional sculpture. It's called Cold Dark Matter, an Exploded View. It's by Cornelia Parker. It's really amazing. And this is what happened when I told my brother-in-law, who was Italian, and I told him, I'm working on dark matter. And he said, oh, actually, I know what that is. And he showed me this picture. He took it and it turns out you can buy dark matter on the internet. Apparently, it builds muscle mass and costs about $44 for 20 servings. The big jar, I've actually seen one of them once. It comes in blue raspberry fruit punch or grape flavors, and I don't know what that means, but it sounds pretty important. I will note that the other kinds of matter we know, the ordinary matter, all comes in 3 copies of things that look identical. So if the dark matter does also come in 3 copies, I think we have to agree that these are what we're going to label those 3 copies. Now, another thing that I noticed actually when I was looking at making this slide is that this is still cheaper than a sandwich in Aspen. And also, the price used to be $60 in 2015. So apparently dark matter is the cure for inflation. Somebody should tell the Fed. You can also buy these adorable little beanbag toys. They're also dark matter. And they're actually a lot cheaper than that other stuff, which probably tastes disgusting given the flavors it comes in. This also shows you that these are great toys. In fact, if you wanted to save some money, you could buy the entire theoretical particle pack, and you'd also get the graviton and the tachyon as well. Okay. Everyone's heard of ChatGPT, right? This is what ChatGPT thinks dark matter is. I don't think I'm going to read it to you. I will observe, though, that the basic description it got sounds a lot like what I just told you. And I just did this morning. So this is not, I'm not copying it. It might be maybe copying me, depending on how it was trained. It says that dark matter could be weakly interacting massive particles, axions, sterile neutrinos, dark photons, theories that modify gravity or have extra dimensions. And basically it says, despite our ongoing efforts to understand dark matter's nature, it remains a mystery and we have to keep searching. So the rest of this talk is basically going to be telling you how we're doing that and where we stand in terms of that journey. I'd like to do an experiment first. You'll indulge me. And I'm a theoretical physicist. I've never done an experiment before. And so if this fails, I'm going to be terribly, terribly crestfallen. You take out your phone and scan this QR code. You can actually type in a word that you think describes dark matter. I'd just like to see what we come up with. I'm going to do it too, but I'm going to put in the very uninspiring word dark. Is it working? Oh no.
Scroll down. It's there. You just have to scroll down.
Scroll down.
Yeah, scroll down.
No, I don't.
There's the word.
Okay, that's weird. How about I'll do this. I'm pretty sure I can reactivate it for us.
You can still do it. I haven't submitted.
If you're doing it now, it won't stop you. So go ahead if it's working. Okay, what do I need? I need stop sharing that. I need to start sharing. No. Start sharing. We don't know what happened.
Okay. You can just type minty.com.
That's right. You could also type it in. So now I want to play this. And I want to make it. Okay, so the QR code is still there if you want to keep putting your words in. Seen great things already, like fantasy. That one I haven't seen before. Faith. Flavorful. Really, it's grape flavored. And of course, you know how these word clouds work, right? The bigger words are the ones that more than one person is typing in. So clearly the message that it's mysterious, that it's dark is actually coming through. AK mode, I think this is one of my physics colleagues actually put that one in. Right, well, Everyone satisfied? Raspberry, all right. Great. This is a great set of results. Now I'm going to stop sharing that. Oh no, what happened there? Here we go. Go back to the presentation. Okay. This is what happened when I asked a bunch of my Facebook friends and a Slack channel. Don't know what that is, it doesn't matter. A bunch of physicists, what they thought about with dark matter. And we got actually 104 responses. See that some of your responses are actually the same as their responses. I don't even think those are the ones that the physicists in this particular room typed in. It's a very interesting exercise. You can also see that the same things came to the forefront. The fact that it's invisible, the fact that it's mysterious, the fact that it's cold. That's how physicists usually say the fact that it's not moving very fast. Then a bunch of things like WIMPs or axions that ChatGPT knew about as well. So I wanted to point out a few of these. This person is clearly a jerk and is dead to me. This person must have heard about the other person typing in what they typed in. Luckily, I got one of each. So, I wanted to give you the caveat that maybe you shouldn't listen to what I say. And then there's a bunch of very interesting things like a bank error in your favor, which kind of does sound like what I described with the galaxy earlier. Darth Vader, that's clearly where his power comes from. It's annoying or it's exciting. My attitude is actually it's both. Okay. The answer that I worked on when I was younger was that it was photons trapped in a tiny wrapped up dimension. See, I look a lot younger. This is actually a picture that I built in 2013. This is a Venn diagram. So everything in a circle is the name of a theory that physicists have proposed to try to explain what dark matter is. When the circles overlap, that means that they have things in common with each other. And when they're inside one another, that means that actually one of them is a subset of the other one. It was fun. It came about actually because an actual experimental particle physicist asked me how a few of these theories were related to each other for symmetry, the PMSSM and M-Sugra. And then he said, well, this is too complicated. Can you make a Venn diagram? I said, sure. I don't know if the value is actually science or abstract art, but it is very interesting and it shows that we have really been spending a lot of time trying to figure out what dark matter is. And I wanted to point out that actually a lot of that happens here at the Aspen Center for Physics. Every year when I'm here, I end up talking about models of dark matter with other people. And often there are papers that come out of it. So this is a great thing that the center does for us. So I'm going to go out on a limb and say, that's all great. It's beautiful. It's wonderful. And that is way too many theories. Given this huge space of theories about dark matter, I'm actually not going to get into what they are anymore. Instead, I'm just going to talk about how we can determine which one is correct. Because I think without some kind of guidance, we clearly are not converging. We're having a lot of fun and learning things too. So what I'm going to talk about is reorganizing the problem. Since there's too many theories, I'm going to reorganize it by grouping theories together based on their common properties. And the two properties I'm going to use are the dark matter mass and the interaction strength of ordinary matter. So every single point in this plane, red and the green areas, are different places where the dark matter could actually live, and that would be the theory of dark matter. And that tells you then how heavy it is and how much it interacts with the standard model, with the ordinary particle. So, for example, the mass of the dark matter is indicated along this axis up here at the top. This is a pretty non-intuitive plot. It's actually on a logarithmic scale. And so that means that every little tick is 10 times bigger than the one before. If I were to look at this particular tick and call it 1, this one over here, 3 ticks away, is actually 1,000 times bigger. And the next one over is 1,000,000 times bigger. And then trillion, quadrillion, quintillion, I don't even know what to call it. Going the other way, we call this 1, 1, this would be 1,000th, 1,000,000th, billionth, etc. So this is a huge parameter space. The number of possibilities here is far more than a human brain can really conceive of. And the vertical position indicates how strong the forces between the dark matter and the ordinary matter are. At the top of the diagram, stronger than the strongest force we know, which is the strong nuclear force. And at the bottom of the diagram, they are as strong as the weakest force that we know of, and that's gravity itself. And we know dark matter has to interact through gravity because that's what made it turn into galaxies. If it helps, another way to look at the strength of the force is how far a particle would typically be deflected if it passed nearby. Remember the example of the two electrons, and they deflected away from each other because they were throwing photons at each other. That tells us what the strength of the force is, the amount that the electrons get curved away from just passing by each other and not realizing the other one is there. We can look for analogous processes in which the dark matter is trying to influence ordinary matter. And of course, that should be accomplished by exchanging some other kind of force-carrying particle. And that could just be a dark force. It might actually be something else that we don't really know much about. So that would be an opportunity to learn about that as well. So, of course, this is a really big landscape, places where dark matter could live. It's a little overwhelming, even reimagined in this way. And what we've done here is we've indicated regions where some of our favorite theories, so you remember Axion, that was one that both ChatGPT and the physicists liked. Sterile neutrinos, that was actually one the physicists said, but I didn't point it out. And the WIMPs live over here. So that's why we've actually shaded them. Now, that doesn't really mean we have any evidence that these theories are better than the other parts of the space. What it means, though, is that these areas typically solve some other problem. And so if you can solve two problems with one dark matter particle, that would make you happy and be economical. And maybe nature even works that way. So what I'd like to tell you about is how these searches are going. And I'm going to show you the answer or the current situation first, and then I'm going to go back and tell you how it looks this way and why it looks this way and how we're actually doing it. We're making headway. So what we've done here is we've shaded in all this shaded region. There's a little island down here, places that we've already managed to look. We haven't actually found dark matter. And so you can see that some of our favorite theories, we've really made an effort to target them to try to actually see if the dark matter is there. And so far, we haven't found it there in those places that we look. Of course, there is a lot still unexplored. Or more is still unexplored than is explored. And unsurprisingly, there are a lot of physicists who want to search for dark matter. Whoever finds it is probably going to get a Nobel Prize. So that's a pretty good reason. Also, it's a lot of fun, and physicists largely do physics because they find it fun. There are many different experiments that are looking for it. In the remaining time, I'm going to say a little bit about how a few of them work, and then show you what they actually are telling us about that space of parameters that we saw. So I'm going to start with a very popular strategy to look for dark matter, and that's to look for the dark matter that we think is flying around us, right? Our galaxy is made out of dark matter, and that means that there's dark matter right here. It's entering the atmosphere, it's passing through us right now. It interacts so weakly that we don't even notice that it's there. And so that's looking for this kind of scattering that I was talking about, where the dark matter comes in, some ordinary matter comes in, exchange some kind of force, dark matter goes off on its merry way, the ordinary matter is deflected. The thing is that we can't really detect the dark matter. And in fact, if you want, this is how we detect the dark matter, is by seeing the ordinary matter get deflected. And this strategy is called direct detection. This is another graphical way of showing it. You have ordinary matter coming in, dark matter coming in, something happens, and they get deflected and go out in different directions. So the way that direct detection works is usually by taking a large number of atoms, that's the ordinary matter that we're using to detect it, and shielding them from external radiation. And the easiest way to do that is actually to just put your detector very far underground with a lot of rock. That helps keep a lot of ordinary radiation from getting down to you. And also building shields around the detector itself. But if anything does manage to get through the rock, at least you can see it go through the shield. And therefore you know that it's there and you know it's not really dark matter. Dark matter itself typically go through the rock, through the shield. If you're very lucky, the only place that it actually does anything is with one of your targets. Target actually starts moving as a result of being bumped by the dark matter. Dark matter goes off and you don't even see it go off. You get to see this particle moving. So that's what we're looking for. It's almost Zen in a way. You have a bunch of things that are just sitting there doing nothing. And the signal is they start doing something when there is no external agency that seems to cause that to happen. Some interesting features about the kind of signal you'd expect to get. That comes from the fact that the motion of the sun and the earth, right? So the sun is kind of going around our galaxy in a kind of a lazy way. It takes like 1 billion years with one bit of the galaxy. The earth is going around the sun, and of course it goes around every 1 year. And the point is because the sun is moving around the galaxy, we effectively see a wind of dark matter particles coming towards the sun. So that means that if we could actually see the direction the dark matter was coming from, these experiments typically are not really looking for that. But if we could, we would actually see that they're not all, but they're on the average coming more from one direction than from the others. However, the Earth, which is where our detectors actually live, is also moving around the sun. So that means that for half of the year, the Earth is going in the same direction as the sun is relative to the galaxy. So in that case, the wind seems a little stronger. The other half of the year, the winter, in fact, Earth is going in the opposite direction as the sun. In that case, the wind seems a little bit weaker. And so that tells you, that's something about the signal that you could use to try to determine whether it comes from dark matter or from something else. There's a lot of things actually on the Earth depend on the season. This one, though, doesn't depend on whether you're in the north or south hemisphere. So at least it's different in the northern hemisphere from the southern hemisphere. So I'm actually going to show you a real plot that physicists use to talk about this kind of search. It's very similar to the plot that we saw before. It's got the dark matter mass, something to do with the interaction strength. Just as a reminder, here it is, right? Heavier masses are going this way. Stronger interactions are going up here. Every point is a place the dark matter could live. And the shading is telling us what our experiments have actually managed to accomplish in terms of looking for it. So far, we built these detectors. In fact, we had a whole session this morning in our workshop where we talked about the type of detector and the searches. Build the detectors, we operated them. We're still operating some of them. Haven't seen a signal yet. And as a result, you can actually say something about where the dark matter can live or is not allowed to live anymore. And the current technology is largely focused on big canisters of liquid xenon. So here's one example, the LZ experiment. This is what the canister looks like from the outside. See, the canister is in here. This is even pulling around it. Inside the canister, there's liquid xenon. The idea is the dark matter comes in, it bumps one of the xenon atoms, it starts it moving, and that produces a disturbance in the liquid, which is then read out by detectors, the top and the bottom. They're looking for a signal. And one of the things they're looking for is electrons, and the other one is actually just light that gets released. Building bigger and bigger canisters has enabled us to make a lot of progress. As of 2013, we've kind of taken a bite out of the space like this. So it only works for dark matter masses bigger than 1 GeV, or about the mass of a proton. The limits get weaker as we go to larger and larger masses. They also get weaker if we try to go to lower masses too. But as of 2013, about 10 years ago, we'd excluded this wedge. And then as of actually last year, we'd excluded all this thing. If you look at this, if you look at the y-axis of the plot, which is telling you something about the interaction strength, and you look at the most sensitive point, which is a mass of sort of around 50 times the mass of the proton, you can see that we've gone from about 10 to the minus 45 down to 10 to the minus 47. That's like 100 times. In other words, we put a limit that the dark matter interaction strength with ordinary matter is 100 times weaker than what we knew it was allowed to be 10 years ago. 100 times is a lot of progress. There are still detectors operating, and there's more progress expected actually to be coming soon. And that's what this green region is showing you. It's showing you where the detectors that are already built and are currently taking data are actually moving down. And we think if they don't see anything, of course, if they see something, we're not going to say this is excluded. We're going to have a big party. But if they don't see anything, we're going to say this much is excluded, and at least we know not to look there anymore. There are also plans to build new detectors, and that will actually get us even more sensitivity way down here. So now compared to that point we had 10 years ago, we're actually something like 10,000 times more sensitive. There's a challenge coming, and that's indicated by this shading in the plot, this sort of gray region that is called EE, right, is the chemical symbol for xenon. This is the neutrino fog. At some point, our detectors built out of xenon become so sensitive, actually they can see neutrinos that are already around us, and that our detectors are just not sensitive enough to see them now, but at some point they'll start to actually register them. At that point, we're going to actually, the detectors are going to stop seeing nothing, and they're going to start seeing xenon atoms getting pushed around by neutrinos, and that will make it easy to hide a dark matter signal. There are new ideas, like using that information about the direction the incoming dark matter is coming from, can help us distinguish dark matter from neutrinos. That's what the yellow region down here indicates. And there's also new ideas for new technologies, like, for example, quantum sensors that are sensitive to very, very tiny amounts of energy being deposited in them. That actually makes it possible to see dark matter masses well below what the current detectors have been able to see. So these are new technologies that are not based on xenon. One example has this great name of INSEE. This kind of cartoon-like plot I showed you of our progress overall actually secretly was encoding the information in the plot that I just showed you from the direct searches. See this little bump here? That's actually that thing. That's what this did. It actually managed to shade this out. It also gives you some context that this whole plot that we were looking at before is only a very tiny piece of the big puzzle. But we need even new ideas to actually look into the rest of it. And so, for example, if we want to look at ultralight dark matter, at some point when the dark matter is light enough, there has to be so much of it to produce enough gravity to explain our galaxy that we stop seeing it as like single particles that come into the detector. We actually start seeing a whole bunch of them constantly moving through it at all times. At that point, the dark matter doesn't look like someone shot a particle at your detector. It actually looks like a wave is moving through the detector, a wave of stuff. And so there are special resonant antennas that have been built to sweep through possible frequencies and look for the signal. Here's one example that exists called the ADMX experiment, and it's managed to make some very nice progress looking for the QCD axion down at these very, very tiny masses. One coming in the future is called dark matter radio. An update about that this morning. There are also different kinds of searches for dark matter. So indirect detection tries to see high energy particles of ordinary matter that are produced when the dark matter annihilates. Remember, before, the dark matter was actually pushing on ordinary matter, and we were looking for the push. Dark matter could also just find one of its friends, they can get together, and their mass has a lot of energy. Remember, Einstein said E equals mc squared. We can take the mass of the dark matter and convert it into ordinary matter at high energies. And so this is another way to try to look for dark matter. One example is something called the Fermi Large Area Telescope. We usually abbreviate as Fermi because flat is not a very good acronym, which is looking for gamma rays, and that's high energy photons. Here's a little cartoon that shows you how Fermi sees a big part of the sky at all times as it orbits the Earth. It's actually a satellite that's looking for these gamma rays orbiting the Earth. So if we ask, okay, what is Fermi doing for us? It's actually telling us about the higher masses here beyond. So here's what the xenon experiments told us, remember, was a little bump. Fermi is actually managing to tell us something about what's happening here. And again, they don't see a signal yet, so we haven't actually discovered dark matter, but at least we can say it doesn't live up here. You can also look at collider production, and this again is using Einstein's E equals mc squared. We can take high energy protons at a particle accelerator like the Large Hadron Collider, smash them together in the hopes that the quarks inside them will find each other, and now we're turning the energy in the protons into the mass of the dark matter particle. So there's a whole bunch of detectors that look at the results of LHC collisions, and they're sifting through those, looking for signals of dark matter. I'm not going to go through them in great detail. Like I said, there are several of them, and they're all actually doing very interesting things. I'm just going to mention the phaser experiment because that was designed actually and built at UC Irvine a few years ago. It is now actually collecting data. And it had a big triumph in the last few weeks. It actually saw the first neutrinos that had ever been seen produced by the Large Hadron Collider. It's sensitive to neutrinos in the same way it's sensitive to dark matter. And we can ask then, okay, what is phaser doing? Well, phaser is helping us down here in this intermediate mass range. So all of this stuff is actually being excluded as a possibility. A set of different kinds of experiments doing different things. You put them all together and you actually get a picture of where the dark matter can't live. And then finally, we can also go back and try to learn more about dark matter from telescopes. If we measure the shapes and positions of galaxies, it can tell us if there are dark forces that just let the dark matter repel or attract itself. No ordinary matter required. In that case, it can change the way that the dark matter clumps together to form galaxies. Gravity tells us about the big structures in the universe. So this is the same kind of picture we saw before, where there's a cluster of galaxies here, or filaments of dark matter linking it to other clusters of galaxies. If gravity is the only thing working, then you're going to get these nice, very dense galaxies where the centers are have a lot of dark matter in the middle. The dark matter repels itself. It can't actually cluster into such dense objects, and instead it forms galaxies that are more puffy. So just looking at the shapes of the galaxies can actually tell us, does it look more like this or does it look more like that? So far, it looks more like only gravity. And this is the Vera Rubin telescope, which is going to come online in a year or two, and it will start advancing this type of study as well. And it's telling us actually something about the part down here in the green. These cosmic probes help with dark matter that have important dark forces among itself. So, almost finished. What does all of this work buy for us, right? This is literally the effort of thousands of physicists over a few decades. What is it actually telling us? It's actually doing a lot. So we've seen what it's done for us today. All these experiments that are still running, what are they going to do for us in the near future? The answer is they're going to make major bites out of the parameter space. They're going to be able to be sensitive to dark matter living in all sorts of different areas. You can just go back and forth so you can see the difference again. This is actually a lot of progress. Of course, we're not really doing this to just say, well, the dark matter doesn't live there, and it doesn't live there, and it doesn't live there. We want to know where the dark matter does live. And so every time we extend this gray shading, what we're doing is finding new places where if the dark matter were there, we would actually see a positive signal and we'd be able to detect it. And so what I've shown here, of course, anything really wasn't explored before, but is going to be explored in the near future, is a candidate for where that could happen. You can see that this stars indicate some possible places, just chosen kind of randomly, and they really live in all different parts of this space. What we have is a really broad program of searching for dark matter. It uses lots of experiments and lots of experimental ideas. And what it does is it covers a huge amount of theory parameter space. That's the wide net. We're constructing it, and we hope that we catch something. Now, someone coming in this afternoon said, well, if you're trying to catch dark matter, shouldn't it be a fine net? It's true. Unfortunately, I don't think we can build one fine enough. So let me just sort of wrap up and say what we found. We know there is dark matter. Don't know what it is. Finding out how it relates to our current model of particle physics is very important to tell us about basic building blocks of the universe. We have different ways to try to measure its interactions. We talked about seeing it interact with ordinary matter and targets deep underground, seeing it annihilate in our galaxy and sending high energy ordinary particles to us, or producing it at a particle accelerator like the Large Hadron Collider, or measuring the properties of galaxies with telescopes. And what we find may surprise us. This is firmly in the realm of science fiction, but dark matter has dark forces. Maybe there are dark matter physicists, and maybe they're trying to figure out what we are. Or maybe they're kind of annoyed that we're not actually asking the right question. Thank you. You have been wonderful. And I'm going to leave you with my favorite.
Very challenging, after. I think we can hold some questions on the audience. Yes, please.
So for direct detection, when you said when you said that they repel each other, do they repel each other like forces repel each other?
The question was, in direct detection, I said that they are repelling each other. And you're asking if they repel each other like charges, like two negative charges repel each other. It actually doesn't matter. It can do either one. So either it can track the xenon closer towards it and start it moving that way, or it can push it away and start it moving the other way. These detectors really only care that the xenon was sitting still and then it starts moving. So it doesn't matter what direction yet. Now, of course, I said that someday it would be nice to know what direction the dark matter was coming from. Then your question would become operative, because if we then knew it was attractive or repulsive, we could reconstruct where the original particle came from. That would be more information about it.
I wasn't really asking about for xenon specifically. I was asking more about when you showed that graphic of two particles, and for direct detection was the first one. When you said they repelled, is it like a repelling? Yeah, that one. So is it like a repelling force, or is it just any movement at all?
So any movement would work for this type of experimental search.
Okay, thank you.
Yes, please, go ahead. In your lecture, you mentioned about 6 billion years. In that incurring period, and the thing that wasn't mentioned tonight, you know my bent, black holes, which are massive, and with the demise of a black hole, might not new matter and new energy be produced from the demising. We're seeing two black holes within a period of time are colliding. That might present tremendous evidence. Also, there's a paper out where observing a black hole and dark energy around it. I brought it along with you, like here. That gives me even more feeling that tremendous energy in a black hole, which might be part of the answer. Any thoughts?
So yeah, so the question is about black holes and whether they're relevant for dark matter. I'm going to paraphrase. And that's a great question. So there's a number of ways that actually dark matter and black holes could be very closely related. One of them, for example, is it might be that the dark matter is in the form of some kind of black holes themselves. Well, I'll get to that in 1 minute. It may be that the dark matter is actually black holes. Now, these would have to be kind of unusual black holes. They would be black holes that were produced very early in the history of the universe. They wouldn't be the ones that are forming from the demise of stars like we're seeing now. So Alex Kusenko, sitting here in the front of the room, is actually an expert on that topic. He's smiling now. That's one idea. Then you also mentioned the demise of black holes, and that's also very interesting because black holes, if they're too big, radiate Hawking radiation.
Isn't that so minor that it's not?
Not necessarily. It may be that that Hawking radiation is the main way the dark matter got produced in the universe. That's one possibility. And you also talked about this interesting result that I don't know that much about, but I know what you're referring to. Yeah, we can talk about that on Facebook.
All right. Yes, please.
So you were talking about neutrino detection and how that's kind of eating into the space. So how do these kinds of experiments differ from neutrino detection?
That's a great question. And they actually look very similar in the sense that neutrinos also have very weak interactions. If you had to make a cartoon of a neutrino detector, it actually looks a lot like this. Now, neutrinos have electroweak interactions, which we think are probably larger than the interaction that dark matter has with ordinary matter. Neutrinos are easily, then we think that's why we can see neutrinos. That's why they're more easy to detect right now than dark matter is. So the directional aspect comes in terms of how particles are produced and where they're coming from. So dark matter, right, is largely coming because of this dark matter wind. And so it comes from a direction in the sky that changes, of course, as the Earth goes around the sun. But we can figure it out at any given day, and we can say, okay, today it's that way, then it'll sweep across the sky as the year goes on, until eventually it comes back to that same day the next year. Neutrinos are mostly produced in the upper atmosphere by high energy particles interacting with air, basically with stuff there. They come from up, they go down. Now, of course, neutrinos are also weakly interacting. Some of them get produced on the other side of the Earth, and they punch all the way through the Earth and come up. They come from either down or up. That's typically not the same direction as the wind of dark matter is. So that's why this idea to try to go into the region where neutrinos start to become a problem is focused on being able to reconstruct the direction the dark matter came from. Because then you can ask, is that magic point in the sky where we think the wind should come from? Is it straight up or straight down? And you throw away the ones that are up and down.
Any other questions? Yes, go ahead. What is your current favorite candidate?
So the question is, what's my favorite candidate for dark matter? I'll tell you, I made this diagram in part because I'm a very strong agnosticist. And so I didn't want to take a point. I think many people could have made this diagram, but they didn't do it because they only wanted to put their favorite on there. when I started working on dark matter, I worked on something having to do with packed extra dimensions. That's what I was saying in the picture of me. It does live here, over here. It's these theories here. I think I still have a warm place in my heart for them because of the fact that they were the first ones I worked on. So, you know, it would take any single one of these.
I may have misunderstood, but did you say that when two dark matter particles collide, ordinary matter is created?
So the question is, if two dark matter particles collide, is ordinary matter created? Yeah, so that is actually a possibility. We think that is likely to be something that happened.
There are a lot of ordinary matter being created.
That's right. And then the only question is, do we have detectors that are sensitive enough to see it? And can we tell it apart from the rest of the ordinary matter that's already there to begin with? And it's that second question is the big challenge for that kind of search.
Yes, please.
Yeah, I may be wrong, but it seems like science doesn't really know exactly what gravity is. I mean, you know, there's always this warping of the space-time and particles, and could it be that gravity is different somewhere else?
So the question is, could this just be gravity being different somewhere else? And the answer is yes, it is possible. It's hard to fit all of the evidence we have for dark matter with just that idea. And the reason for that is that, you know, if you want gravity to be different, you have to decide, when does it get different? No, Newton's gravity will describe it if I drop this laser pointer, which I'm not going to do because it's expensive. But, no. Then the question is, at what length scale does gravity start to look different from what we have predictions for? And the measurements that tell us about dark matter are on very many different length scales. And so just changing gravity in one place wouldn't be enough to fit all of them, but maybe a complicated theory could change it several times and fit everything. We don't know what that theory is yet, and that's an active thing that people are actually doing research on.
So you guys think about those things?
Oh yeah, absolutely. Now there's one back here you might be missing.
Oh.
I know that you wanted to exclude dark energy from the conversation, but for those of us who really need to know, can you just like a very short how it relates to all of the rest of these studies and thinking?
So the question is, what about dark energy? What if we really need to know? So for those of you who need to know what dark energy is, the answer is we actually don't have any idea. We don't even have a diagram like this of ideas.
Okay.
We do make measurements to try to pin down the properties of dark energy. And the idea is hopefully someday it would suggest building something like this.
Okay.
That is still a field that's more in its infancy.
Thank you.
Right now, we're just trying to describe it.
Yes. Funding theories, how does that work? Meaning there's different kinds, different projects going on.
That's right. So you're asking how theoretical research is funded?
Yes, in as much as there's a variety.
That's right. So the funding agencies, so largely the US Department of Energy or the National Science Foundation, they actually have a budget where they use to fund a certain amount of research like mine and like other theoretical physicists. And the Center for Physics, I think, also benefits somewhat from that.
Somebody has to decide which ones.
That's right. And so there's a lot of oversight, as you can imagine. You know, experts get together and they look very carefully at research proposals and say, oh, this one's crazy, don't fund that one. Or, oh, this is great, we really need to do this. And so decisions are made like that.
Any further questions? Yes.
What's your least favorite theory of dark matter?
Oh, do I have a least favorite theory of dark matter? No, I'm not sure that I do.
All right, so that's a good answer. So that's probably the important answer for at the summary of this overall talk. So that's a science. The science is something to explore, something new. We don't know the answer yet. So whenever we make a progress, we make the discovery, and that's the advancement for our science. With this note, probably we should thank Tim again very much. Thank you.
Thank you.
One very quick announcement. Daniel Meissen over here is also going to be, if you haven't had enough physics, tomorrow at Explore Booksellers at 4:30, he will be there answering frequently asked questions about the universe.
I want you all to make it a point to ask him what his least favorite theory of dark matter is.
Have a good evening.